calculating standard free energy of the reaction. So we've learned that this change in free energy is the criteria by which we identify whether a reaction is spontaneous or not. So the standard change in free energy is the criterion for spontaneity at standard conditions. Okay, we already talked about what those were. There's three different ways we can calculate this. We can calculate the standard standard enthalpy of reaction and the standard entropy change for the reaction from tables of heats of formation and standard molar entropies. And then we can use this equation. The Gibbs free energy change is equal to delta H minus the temperature times delta S. We can calculate it directly from Gibbs free energy of formation numbers that you can look up in a table, or we can also calculate it from free energy changes for the steps in a stepwise reaction. So which one you use kind of depends on what information you have available. I think number 2 is probably the fastest, but if you don't have the delta G values, then you can't do it that way, right? So the first way is using delta G equals delta H minus T delta S. So here we're going to calculate the standard entropy change for the reaction and the standard enthalpy change for the reaction from tabulated values. And we're using that somewhat intimidating, right, equation. So that works for delta S. It also works for delta H. Again, it's the products minus the reactants. Once we get those numbers, then we can calculate delta G using this equation. Now, strictly speaking, this would only be valid at 25 degrees Celsius. But it's going to give us an estimate for other temperatures. It's not going to be crazy different at other temperatures. So let's do an example of this one. Consider the oxidation of NO to NO2. Calculate delta G at 25 degrees Celsius and determine whether the reaction is spontaneous at this temperature. We're given heats of formation and entropies. Actually, I don't think the delta is supposed to be there. Oops. So this is the only way we can do it, right? So we have to calculate delta H for the reaction and delta S for the reaction. So delta H is going to equal the heat of formation for the product times how many moles there are. Right, there's only 1 mole of this, and delta H for that, we got to be careful, there's NO and NO2, is 33.2 kilojoules per mole. So we've got 1 times 33.2 kilojoules. Whoops. So that's all of our products. There's only the 1. And then we're going to subtract the heats of formation for the reactants. So we've got 1 mole of NO, so 1 times 91.3 kilojoules, and half a mole, seems a little weird, but it's okay, half a mole of the O2. Well, what's the heat of formation for O2? 0, because enthalpy is defined as 0 for elements in their standard states, and that's what oxygen is. So we're just going to have 33.2 minus 91.3, negative 58.1. And that's kilojoules. I didn't write the moles in here, but we saw in the previous example how they cancel each other out. It is important to keep this kilojoule here because the units on entropy are joules. And so we need to make sure that when we're adding things together, we use the correct units. So for the entropy change, same process, but we're going to use the entropy values. So I've got 1 mole of NO2. The entropy for that is 240.1 joules per Kelvin. And then I have 1/2 mole of oxygen. Oops, forgot where I was going. That's the products. Subtract the reactants now. 1 mole of NO is 210.8 joules per Kelvin. And 1/2 mole of oxygen. And the oxygen's entropy is not 0. It's 205.2 joules per Kelvin. I'm getting negative 73.3 joules per Kelvin. Am I mathing okay so far? We're going to take these values and plug them into this equation. So delta G is going to equal delta H for the reaction, which was minus 58.1 kilojoules, minus the temperature, which needs to be in Kelvin. We're looking at 25 degrees Celsius, which is 298 Kelvin, times delta S, negative 73.3 joules per Kelvin. Those kelvins are going to cancel out. But here's where we need to be careful, because this is kilojoules, and that's joules. So I think it's easier to just put it into joules, and kilo means times 10 to the third. So there we've got joules. So negative 58.1 times 10 to the 3 minus 298 times negative 73.3. And what's my unit? Joules, right? Okay, so that's an awkwardly large number, and it has too many sig figs. So we should probably express the answer in kilojoules, right? So we're going to divide by 1,000, which moves the decimal point over 3 places. So it's going to be negative 36, and doing mostly, looks like in kilojoules, 1 decimal place. So minus 36.3 kilojoules would be a reasonably stated answer. Any questions? Oh, we forgot the question. Determine whether the reaction is spontaneous at this temperature. Okay, now we've seen the answer. How do we determine if it's spontaneous? If delta G is negative, it's spontaneous. If delta G is positive, it is not spontaneous. So delta G is negative, so this is spontaneous. This will happen without interference. Whoops. Okay. Oh, I forgot to put the animation on this one. So, well, there's the answer. estimating standard change in free energy at a temperature other than 25 degrees Celsius. Again, using delta G equals delta H minus T delta S. So for the reaction for practice 19.6, right, calculate the value of delta G at negative 55 degrees Celsius. Is the reaction more spontaneous or less spontaneous at the lower temperature? And so here are the values that we calculated earlier, so we don't have to do them over again. So delta G is going to be delta H, negative 58.1 kilojoules. Well, we're going to need to put that in joules anyway, so we might as well just do it right now. Times 10 to the 3 joules. Minus the temperature. Okay, probably not a good idea to do this one in your head. Negative 55 plus 273, 218 Kelvin, times delta S, so that would be negative 42.1 kilojoules, which conveniently matches the answer up there. Any questions? How do we tell if this is more or less spontaneous than the previous one? Is it more negative or less negative? Like, well, that was negative 36. This one's negative 42. This is more spontaneous at the lower temperature. So calculating delta G using tabulated values of free energies of formation. So just like we calculated delta H from delta HF, we can do this with delta G. So the free energy of formation is the change in free energy when 1 mole of a compound in its standard state forms from its constituent elements in their standard states. The free energy of formation of pure elements in their standard states is 0. So delta H and delta G, elements in their standard states, are 0. Delta S, nothing is 0. So again, we've got that same type of equation here. Find the delta G's for the products and subtract delta G for the reactants. One of the reactions that occurs within a catalytic converter in the exhaust pipe of a car is the simultaneous oxidation of carbon monoxide and reduction of nitrogen monoxide, both of which are harmful pollutants. So use standard free energies of formation to determine delta G for this reaction at 25 degrees Celsius. Is the reaction spontaneous at standard conditions? So here we've got delta G, standard molar free energies of formation for a bunch of things given there, and it actually does include all the things we need, so that's nice. So delta G, I'm going to look at the products first. 2 moles of CO2. So we'll go over here and find delta G for CO2, negative 394.4. That's kilojoules. And for nitrogen, Well, nitrogen is an element in the standard state, it's 0. Okay, so we don't have to do anything there. So those are the products. And now we're going to subtract the reactants. 2 moles of carbon monoxide. 2 times delta G for carbon monoxide, negative 137.2. And 2 moles of NO. And the nitrogen monoxide, where'd you go? You're over here. Plus 87.6. You don't have to put the plus there. They do that just to call attention to it, I think. 2 times negative 394.4 minus, parentheses, 2 times negative 137.2 plus 2 times 87.6, close the parentheses. And delta G is going to be negative 689.6 kilojoules. Is the reaction spontaneous? Yeah, it is. Any questions? Oops. Okay, the third way of calculating delta G. So delta G, the free energy, is a state function, and so we can use Hess's law and take different chemical reactions where we know delta G and add them together to get delta G for the new equation. So the same relationships for enthalpy apply to free energy. Okay, so these are different than for equilibrium constants. If the chemical equation is multiplied by a factor, then you multiply delta G by the same factor. If you reverse the equation, you change the sign on delta G. And if you can express the equation as a series of steps, then delta G for the overall reaction is the sum of delta G for each step. So find delta G for this reaction. Use the following reactions with known delta G values. I've found that it's useful to highlight these things because everything's NO, right? So there's N2O, and then I'm going to go down here and find N2O. Okay, that's the only place. And then maybe I'll use yellow for NO2. It's not confusing at all. This is NO2. Oh, that's the only NO2. And then maybe we'll use blue for no. Where's the no? We've got no here and no there. And then there's nitrogen and oxygens in there, right? These are not going to show up in our final equation, so they better cancel out. What I like to do is just start with the first reactant, and I'm going to find the chemical reaction that has that compound in it, and I'm going to make sure that it's on the correct side of the arrow. So I've got 2N2O gas is going to make 2N2 gas plus O2 gas. And I'm going to highlight that to just remind myself of what's going on. Does this have the same coefficient as in our final reaction? No, it doesn't, right? So let's fix that. So to get 2 to be a 1, we need to multiply by 1/2, right? And when we do that, this becomes, I'm not sure how to indicate this. So that becomes a 1. And I'm going to multiply this by 1/2. So that also becomes a 1. And this guy gets multiplied by 1/2 and it just stays 1/2. So over here, I'm going to keep track of my delta G's. So it was negative 207.4 kilojoules. That doesn't look very good. I multiplied the equation by 1/2. So what do I do to delta G? Multiply it by 1/2. So this times 1/2. Because the free energy change will be half as large if half as much stuff is reacting. So now I'm going to look for the yellow one. So here I've got the yellow one, but I want that to be a reactant, so I'm going to write this equation backwards. So I'm going to have 2 NO2 gas, and on the other side I'm going to have 2 NO plus O2. What do I need to do to delta G? Because I reversed the equation, I need to change the sign. So that negative is now a positive. Is this the correct coefficient to get this equation? No. So I'm going to have to multiply by 1/2 again. Or, if you'd rather divide by 2, that works also. So that becomes a 1. That becomes a 1. This becomes a 1/2. And I did it to everything else. I need to do it to this as well. Now let's keep up with the highlighting so we can see what we've got. So there's the NO2. And I also have some NO over here, and that was the blue one. So I've used this, I've used this one, and I've used that one. We're only going to use each of them once. So I have NO on the product side, but I want 3 NO on the product side, and I don't want this oxygen. So, you could say, well, multiply this by 3, but then that's going to mess this up. We need to use this equation. It's in the right direction. It's got that as the product. So let's write that down and see how that's going to work. We've got N2 plus O2 making 2NO, and delta G is plus 175.2 kilojoules. So when I add these together, I've got 1 no here and 2 no's here. That gives me 3 no's, right? Let's look at what happens with these things that we want to go away. Here I have 1/2 mole and 1/2 mole. That's a total of 1 mole of oxygen, and I have 1 mole of oxygen over there. This is 1 mole of nitrogen, and there's 1 mole of nitrogen over there. So those guys are going to cancel, and this guy's going to cancel out. I didn't multiply the coefficients by anything, so I don't need to multiply delta G. Now I'm just going to pull things down N2O gas plus NO2 gas makes 3NO gas. So delta G for this is the sum of those things. 0.5 times negative 207.4 I had an ugly K in there that disguised itself as a 6. Doesn't belong in there. Negative 207.4, and then I'm going to add 0.5 times 71.2, and then I'm going to add 175.2. And I get 107.1 kilojoules. Any questions? I think highlighters or different colored pens or something, you know, if you like those, this is a place to use them. .1 kilojoules. Okay, here's the big question. Why free energy is free? What do we mean by that? Well, we often use the energy released by a chemical reaction to do something, to do some work. So the combustion of gasoline is used to move a car, right? The change in free energy for that chemical reaction represents the maximum amount of work that's possible or free, maximum amount of energy to do work. So it's the amount of energy that's free to do work. So if we've got graphite reacting with hydrogen to form methane, delta H is negative 74.6. So that energy is coming out, right? But 24.1 kilojoules of that is going to get lost to the environment, to the surroundings, and the maximum amount of work we can do is 50.5 joules. That's delta G. And there's a lot of times where the change in free energy is less than the change in the enthalpy. Any questions yet? So that free energy is a theoretical limit. In a real reaction, the amount of work that you can do is less than that because energy is going to get lost to the surroundings as heat. Only reversible reactions can reach those theoretical limits, and this is something, you know, we do in math, right? We take things and make infinitesimally small sections, right, and add them together and call it integration, right? So a reversible reaction is going to happen extremely slowly, and it's reversible because at any point, if you do the opposite to it, it will reverse. When that happens, the free energy gets drawn out in such small increments that it's going to match the amount of energy that's produced. But does that do any good? No. No, it doesn't. This is an example of a reversible process. So here we have a cylinder, and this disc in the middle is kind of like a piston, and it can move up and down. And it's sitting where it is because there's a gas underneath. And the mass of the sand is pushing down on the gas. So if we take one piece of sand off, is that disc going to move up a smidge? Yeah, teeny, teeny, tiny bit. Probably won't be able to see it, but after you've done that a bunch of times, now you're going to be able to see that there's a change. If you keep going, the thing keeps coming up. At any point here, if you put a piece of sand back on, it would reverse, right? So this is an example of a reversible process, almost, because even a grain of sand is not infinitely small, right? It still has a mass. So there aren't any real reactions that are reversible. So we can't ever achieve the theoretical limit of available free energy. We're always going to lose some. Here's an example of using a battery to run a motor and using a motor to charge the battery, right? So we draw current from the battery to do work with the motor. The free energy comes out, but some of it is lost to heat, right? And isn't useful because there's resistance in the wire. And then you go to charge the battery, it's going to take more energy to charge the battery than you got out of it. So every cycle here, you're going to lose some energy. So any cyclical process like battery charging and discharging, the system returns to its original state, yeah, but the surroundings don't. So the surroundings have taken on energy, they've absorbed, their entropy has increased. It's a permanent dispersal of energy. When energy gets dispersed, you can't just go rein it back in. So if we have a positive free energy change, that means that that reaction is not spontaneous. That doesn't mean it can't happen, but it means that we'll have to use energy to make it happen. So in that instance, delta G is the minimum amount of energy needed to make that reaction occur, but you're always going to need more than that to make a real reaction occur. So that's what's sometimes known as the heat tax, right? You can't win, you can't even break even. Any questions?